In this video tutorial, we're going to discuss the process of modeling, analyzing, and designing a matte foundation in Adapt Builder. Specifically, we're going to be using the module Adapt Matte in RC mode, and the playlist you can find this video at is under Foundation Design in Adapt Builder. We're going to talk about converting a drawing file into a model, setting up springs as supports, assigning material properties, loading, generating design strips, and then meshing, analyzing, and designing the matte. So we're going to go ahead now and get started. We're going to go ahead and launch Adapt Builder. And in the splash screen of Adapt Builder, we're going to select in the pull-down menu here, we're going to turn off Edge and Floor Pro. We'll go ahead and select Matte. This allows us to model a single level foundation system. We don't need the ability to model any post-tensioning, so we're going to select RC only, and then we'll make sure that this is set to the proper units. In this example, we're going to do this in SI units. We'll go ahead and select OK. And in the user interface, we're going to import a DWG file and then calibrate that file. So we'll go ahead and select File, Import, DWG, and you'll notice, by the way, at the upper right, we're working at the bottommost plane. This is by default the bottom of the structure. We have bottom plane, current plane, and top plane. We'll come back and we'll relabel that. But this, when we open the program in Adapt Matte, by default it sets it to the bottom plane. We'll now navigate to the file we want to import from. So we'll go to the DWG files here, and we're going to select this DWG file. I'm now going to choose to calibrate and scale the file inside of the Builder interface. I could also move the file in case it's important to generate an origin. For this example, we're going to not select this. If you do select this, one of the secondary items that will occur is you will have the ability to move the origin of the imported file. And then we're going to insert this at the bottom plane. We're going to call this just CAD1, and we'll select OK. The program is now prompting us to enter the start point of the calibration line. Now this is in feet, so we're going to go ahead and convert that to metric. And I'll go ahead and, using my snap tools from the home menu located here, I could also generate snap options down at the bottom at the user access bar towards the bottom of the screen. We're going to go ahead and we're going to select snap to endpoint. This is the start point of the calibration. This is the endpoint. And now I need to input the distance. In this case, it's going to be in meters. We'll go ahead and just call this 6 meters. Okay, now we want to zoom extents. Now we do have, again, quick access options down below. Zoom extents is one of those quick access options. You can also find these under the home menu, a more extensive list here under zoom and camera. And we can now begin transforming any polygon to an actual structural object. So we're going to say that this polygon here is our actual matte slab. And we'll select the polygon. I'll go up to Model. And rather than adding a structural component, I'm going to transform this region to a matte slab. So we'll go ahead and we'll transform this. Okay, that transforms that to a slab. We'll come back and assign the properties of the slab here in a moment. We're also going to transform columns and walls really just for the purpose of being able to place loads at those locations. They become an easily snappable point that we can reference. So they don't really add much to the overall stiffness of the matte when we're running it in isolation like this, but they do offer an easy way to add point loads or line loads to the structure. So we'll go ahead and select these components. Okay, these are the columns that I've selected. I'm going to transform the columns, and then finally we're going to transform the two walls here. We're going to use transform compound walls. We have additional openings. We're not going to include those in this tutorial. We want to have a solid slab here for the matte. Now once we're done using the converter for the from the CAD file, we can go up to visibility, and that CAD file becomes a group. So if we go to group library, we can turn that off under CAD1. We'll go ahead and turn that off, and we're left now with our model. Let's go ahead and save this. We're going to call this mat model 1. Notice if you need to separate words, use an underscore character. Otherwise, you'll have a warning stating you can't use certain characters in the naming of a file. So we'll call this mat model 1. And if we double click on the actual mat, you can see the thickness here is 200 millimeters. We're going to create a 450 millimeter mat in this case. And we're also going to add a thickening around this core. So we want to have a thickening at that core, and we're going to now input an overlapped slab, what we call a nested slab region. This is going to be a 600 millimeter thick slab where we have these walls. So we want to have let's say an extension of this overlap at some distance away from the edge of the walls. We need a way to actually reference those points, since the CAD file did not contain a polygon where we would model that thickening. We're going to offset the overlap by 1.5 meters from each wall face. So we're going to go back to Home, and I'm going to use construction lines. I'll select the option for construction lines. I want to turn on snap to vertices of components so that I can snap to corners of walls. And if this is not on, then you'll end up snapping only to the endpoint or having the ability to snap only to the endpoint. I'll also turn on snap orthogonal, and this will allow me to draw straight lines so that I can use these lines then to offset and create my slab region. So we're going to select this line. I'm going to go to Modify, and we're going to use Move by Coordinates or Copy by Coordinates. And this is going to be in the positive Y direction. So we'll say it's 1.5 meters. We're going to copy. We'll do the same thing here. This will be in the positive X. This will be 1.5, and enter. We'll just repeat that. Here we have a negative 1.5. And then finally, this will be a negative 1.5 in the X. Okay, now we have some construction lines where we can use. Now under model, we're going to create a slab region. And we're just going to nest this inside of this overall slab region that we converted from the polygon. This gives us the ability to generate some complex geometry in a model. Notice that orthogonal is still on. I can come down here and actually turn that off using the quick access. We'll turn that off and go ahead and create that thickening. Now if we double click on this slab region, you'll notice when I double click, it actually opens the line properties. So if I click once and press tab, it will toggle between the line and the slab. Here I've selected the line, or excuse me, the slab, and we can go to item properties from model. We can select item properties also from modify, and we just need to get that open for that slab in order to create its thickness. So this is going to be 600 millimeters. And to confirm the geometry, I'll go to visibility using the section cut tool. We could take a cut using a start endpoint and an insertion point, and you can see there's our slab region here. Okay, now those lines I might just want to turn off rather than delete. If I wanted to delete them, I could go to Home, Select by Type, Line, and I could select them and then delete them, or I could just select, press Control and pick the lines, or I could also just go up here to the Layer Settings from the Home Display panel. This is also down on the quick access bar, and in Layer Settings I can find the Adapt Line layer, and I can just turn that layer off. And we're left with the slab and the thickening. You can also, from visibility, go to a rendering to look at the rendering of the mat. And this is what we have. And the same process can be used for creating continuous footings, spot footings, grade beams, and so on. Here, this is just an example of a mat slab versus some other type of foundation system. Now, anytime we create a slab that is at the bottommost plane in our structure, and in this case, if we go to the level assignment, the bottom plane is the bottommost plane, we have to have an underlaying support of some sort, which in this case will be soil. So from the Model tab, we're going to select the option for either a point spring, line spring, or area spring. In this case, we're going to use an area spring, and we'll go ahead and I can just create a box basically encompassing this entire model. And now I'm going to double click on that spring and I can assign values for my subgrade modulus in the Z, X, and Y directions. For this example, we're only going to have vertical gravity loads. So really we only need a value non-zero positive for KZA. And we'll just leave this as is, the default. We're going to set this to a compression only spring. If you have springs that are overlapped, for example, if I took a spring and I'll go back to model and I added another spring here, and let's assume in that region we create a bulk modulus or a subgrade modulus of 5.0 E -2. Okay, so now we have springs that are overlapped. This spring is on top of this one. The program will conservatively take the lower value for the spring assignments that are overlapped. If the user wishes to have this region be 5 E -2 and this be 2.7 E -2, then you have to adjoin the springs and not overlap them. So I'm going to go ahead and show you what I mean here. I'll go ahead and open up a marking tool. And rather than have these overlapped, one region might look something like this. This would be 2.7. I would create a second region of 2.7 and then another region of 5. So we have 1, 2, and 3 regions. This is how you would set it up for multiple spring values in a single model like this. Okay, we'll go ahead and delete that. Now from criteria we can assign certain things. We can assign material properties for concrete, reinforcement, steel fiber if you wanted to include fiber inside of the slab. There's options for that. We're going to just leave the concrete material to 26 MPa in this case. The rebar material, I'm actually going to bump this up to 500 MPa. For the yield strength of the reinforcement. The design code we're going to say is ACI 2014. We have the ability when we're working in RC mode, which is indicated at the top. We did not include PT, so this is RC mode. We can also have the program report crack width and also limit probable crack width. If we assume the option for limit, if we assign that, we can limit the crack width to a specified value. And the program actually uses European code EC2 methodology for limiting crack width in that case. Okay, so those options are available. Under the option for shear design, this will be for punching shear. We're going to use the option for studs. And I'm going to go ahead and we're going to use a 12 millimeter diameter stud. The number of rails per side will be dictated really by this setting here. We're going to limit the rail spacing to 2 times the effective depth per side, and then we're going to create uniform spacing of studs. So we have some settings here just for punching shear. We'll go now to rebar cover. We can set the reinforcement cover options for the outer layer, and also this is for top bars and bottom bars, outer layer. Okay, we'll leave these as they are currently for the bottom and top. Rebar size and material, we're going to assign design strips as two-way slabs. We'll use 20 millimeter bars top and bottom. Actually, let's use 22 millimeter bars top and bottom for the reinforcement. The last option here is really for stirrups only, so that doesn't matter for a two-way slab. And then we have options for rebar roundup and rebar lengths. These just give the user options on how the bars are going to be detailed and cut off based on whether it's a bar for minimum reinforcement or a bar for strength. Now in this mat we're going to put a top and bottom base mesh of reinforcement. because of that, there's an option here called bar spacing. What this option does is if the design strip requires additional reinforcement over its width to meet these spacing requirements, it will add additional bars on top of what is actually required by calculation for minimum or for strength. Because I'm going to add a top and bottom mat of reinforcement, that will actually govern and control that. In essence, that meets the spacing requirement. So we'll turn this to disregard maximum spacing requirements. Okay, and we have that now set up in terms of our criteria. Let's go ahead and add some loads. So the first load we're going to add will be just some patch loads, uniform loads on the slab. And we're going to go to load cases. We're only going to be looking today at self-weight, dead load, and live load. The user could add additional loads, load cases, assign loads to those cases, and so on. We'll limit it to these two load cases today. Building loads is something that you will not use for a mat in this type of environment where you have a single level mat. This is primarily reserved for multi-level structures inside of the program. So you'll very seldom use this option when you're working on this type of a model. This option I would recommend leaving as is, leave it blank. We're going to add all of our loads to this up here. Even if you're importing, or excuse me, modeling lateral load reactions like overturning moments or base shears, those load cases should be defined as load cases in the general loads gravity/lateral. This lateral really should be intended for lateral reactions on a foundation. Okay, so let's go ahead. We're going to select our slab region. Why am I selecting it? So that we can map loads to the selected polygon. So we're going to go to Patch Load Wizard. I'll say that the dead load in this case is going to be 1.5 kilonewtons per square meter. And then the live load, we'll use a live load of 3 kilonewtons per square meter. So we have some surface loads. We're also going to generate some loads along the walls. I'm going to create some line loads, and I'm actually going to create a couple of moments at the center of these walls. Let's say they might be overturning moments. And this really would only affect maybe lateral loads. I'll show you how to model it. We're going to avoid using them for the model, but I just want to show you how those can be modeled. Everything else will just be gravity loads. So we're going to add point loads at each of the columns. Okay, we'll add a dead point load and also a live point load. The dead point load will be 700 kilonewtons, and the dead live load we're going to say is 1500 kilonewtons. So I'm going to add a point load. Before I actually place the point load, I'm going to open the properties. So I'll go to modify the properties. And for dead load, we're going to call this 700 kilonewtons. This is an FZ, positive is downward. And what I want to do is I want to make sure that the user understands this is intended to be a unique load, meaning it doesn't, this value cannot represent two different load cases. In this case, we've selected dead load, so it's going to represent the dead load. And we'll go ahead now and add that load. So there's 1 point load, 2, 3, and notice I have the snap tools turned on. Snap to endpoint is what you want on, and that snaps to the centroid of the columns. We're going to just use the same magnitude for each column. It should be obvious how you can change that and assign different magnitudes as needed. If I escape out of that and I go to a 3D view, we can see the loads shown here. Okay, if we go to the loading tab and I show loads, I can visibly turn off all loads. If I want to turn on only the patch loads, this turns on all patch loads. If I want to turn on only the point loads, this is only for point loads. Okay, and then you can isolate the type of load if you use this option for view load settings. We'll go back. I'm going to now add the point loads for the live load. So we're going to go back to modify properties. I'll select live load, and here we're going to say this is 1500 kilonewtons. And again, we'll assign that to each of the columns. Okay, I'll escape out, and now I have my live loads. If I go back to loading display, I can turn on all point loads, or I could isolate one of the two, dead or live. For the line loads, let's go ahead and turn off the loads. I'm going to come back to the plan view, the top view, and for the line loads, we're going to say that the for the walls, we're going to have just a live load. Okay. And the program will also calculate self-weight for these walls, but in this case, we're just going to have a live load for this example. So let's go to the option for add line load. And the line load here is going to be 200 kilonewtons per meter. So before I snap this again, I could snap it and then come back in and double click on it and assign the load. We'll say this is live load, and we're going to say this is 200 kilonewtons per meter. That requires some post editing of the load, so that's why I usually recommend opening the load input box before you place a load. We'll come back to this. Now, rather than go to modify, you can always access the properties on the quick access bar down below, and notice it retains the last value set that was in the load properties, and we'll go ahead and just place additional loads here. Okay. So those are the loads for the slab. Now, if I wanted to place a moment, let's say at the center of this wall, I could add a point load, but rather than adding a gravity load, maybe this is a live load moment, I'm going to add either an MXX. This notation is relative to the global axis set. We have MXX or MYY. In this case, it would be MYY. And you'll notice if we say that the moment is 500 kilonewton meters at the base of the wall, I want to snap on the center of the wall. And so if I click on snap to midpoint, notice that allows me to snap to the center. And then rotating this again to multi-story view, you can see the direction. Positive moment is actually entered as a clockwise sign. So this clockwise positive is the notation for, or the sign convention for the moments. So that's how we would enter moments on the slab. We'll go ahead and go back to our default display. Now, if we go to reinforcement, I want to select the slab, and I'm going to add a top mat of steel. And it's important to understand how this has to be done when you have nested slabs like we've input them. The program will use the slab that was entered first in sequence really as the reference for how the bars are positioned. In other words, the cover. So if I select this over this slab here, the thicker slab is actually at the same plane at the top as the main slab. So it's okay to select the main slab and then assign the reinforcement. We'll go to Mesh Wizard. I'm going to select top. We'll leave the covers as they are for the top. And then we're going to use some bar size here. So we'll use a number 18 millimeter bar. And then for the spacing, we're going to use 450 millimeter spacing for these bars. We'll use the same on the bottom also. So we've created a mesh at the top, and it's symbolized by this symbol here. If you wanted to actually see what the characteristics of the mesh are, we can always go to visibility, where we control the visibility really of all things within Builder. I can come into visibility, and for mesh reinforcement, I'll just put on the dimension, and that will show me the bar spacing and the bar size. Now, if I do the same thing for the bottom bars, let's go ahead and do that. I'm going to go back to model. For the rebar, we're going to model this as a mesh wizard again. We need to select that slab. We'll go to bottom, and this is going to be 85, and we'll say 75 here. And then I'll change the size again to 18 millimeter and create. And you'll notice if I look at the placement of that mesh rebar, if I go to a side view, you can see that for the thicker portion, the bar is being referenced from this slab here upward. This is the 7585, not from this here. So it can't break that mesh into two regions where you have two slab regions. So to get this more precise, maybe I want the mesh down here for the bottom, reference from the bottom of the thicker portion. We have to do this a little bit differently. We have to model it as adjoining regions of mesh, let's say. So we're not going to use the option for Mesh Wizard. We're going to use the option for Mesh here, and we'll go ahead. Once we do that, I'll go. This is like entering a load or any other component where we want to set up properties. I'll go into the Properties menu. This is bottom reinforcement. We have, again, 85, 75. This is just an estimate for the cover. These would actually be adjusted based on the diameter of the bar we're using, but we'll set the bar sizing into 18. Spacing we'll say is 450. Okay, and then we're going to go ahead and we're going to first create a region here, and that region is now referenced from the bottom of that slab. And then I'll also create another region like so. I'm just basically following the points on this slab. We're creating just a polygon that represents the mesh reinforcement zone. Okay, so we'll select this zone here, and I'll actually come over there and click that. I cannot have 2 points touching on the same polygon, so I have to create this third region. We'll press enter, and then the third region will be something that looks like this. There's the third region. Okay, and now if I select these different regions, let's select this one here. That's highlighted. I'll go to a side view again. Now for this particular region, we can offset relative for this lower mat. So let's go ahead and isolate that. Again, I'll show you how to isolate regions. We're going to isolate this mesh rebar and this slab. So I'm going to go to visibility. I'll go to show selection. It hides everything else, and I actually hid the wrong, mesh rebar. Let's go back to rebar and show the rebar. Let me select that one again, and I'll come back and I'll hide that. Okay, and we're going to hide these two objects also. Okay, now we're left with what we want, and I go back to a side view. Now this is still referenced off of the upper slab. The upper slab is 150 millimeters less than this thicker slab. So I need to adjust these by 150 millimeters. And here we're going to set this then to 225 and 235. And it should be negative actually. So if we have 75, 150, this should be negative 75, I'm sorry, and negative 85 because we're going downward. Like so, okay? And that's how we obtain the proper depth of the reinforcement within that zone. Now to get everything back in view, we'll just select default display. To set up the default display, we can go into view settings, select the objects we want to set as default, and use this option save as default. And every time you select default, it goes back to that view. Okay, before we actually start adding the design strips to design this, we're going to check punching shear. We're going to just run a general analysis and look at the soil pressure. So we might want to make adjustments on the slab thickness, if our punching shear and or soil pressures and displacements don't look reasonable. So we'll go ahead to select analysis. We need to mesh the slab in order to analyze it. We're going to use our default meshing settings here, simplified for slabs, and we'll use the 1.5 meter size. We'll select save and mesh. This will create a finite element meshing pattern for us, and then we're going to execute the analysis. And everything that you see on this side really does not apply to this instance or this type of mat modeling. This actually could apply to a mat design if we had a multi-story structure and, for example, we needed to import or include reactions on top of that mat. in the same instance of using the program. So this is covered in a different video where we have both edge and matte in play rather than just a separate matte model in the software. So for this model, we're not going to be using any of this. We're going to use the default load combinations to evaluate this. We have a couple of service combinations and also 2 strength combinations. Again, the user can add additional combinations from loading load combos as necessary in order to evaluate the different service and strength conditions. So let's go back and execute this. Okay, we'll select yes to save the model. And we're interested really in 3 things. We're going to look at the displacement, the soil pressure. I'll show you how to look at those 2 items and then run the punching shear check. First thing I want to do is clear the model from this showing the actual elements. So I'll use the default display again, or I can go to the option for analysis, visibility, and turn off shell elements. These are shells. Those turn off and on using these display options. In the result browser, we're going to select for bearing pressure and for displacements, we're going to use service level load. So I want to select service total or service sustained. These are going to be presented as contours. Contours can only be reviewed in isolation, meaning we cannot envelope a contour. So in this case, we'll select one of the service combos. I'll go to analysis under slab, deformation, Z deformation. This will give us indication of the displacements. So we can see the max displacement is about 26.89 millimeters, which is shown out here. If you wanted to change the way that this is presented, we can go over to settings. We have several setting options here for example, for units, significant figures, diagram results. In this case, we're going to select fixed range versus gradient, and that just changes the way that this is presented on screen. So you can have a color range versus a color gradient for the results, for contours. Again, our max displacement is around 27 millimeters. If we go back to analysis under slab stress, we're going to look at the soil pressures. And we can see the maximum soil pressure here is 2.19 megapascals. And this is, again, negative is in compression. Okay, so this is the compressed corner here where we're just pushing into the soil. We have a rather heavy load there. And we could use this to determine whether or not we exceed some allowable bearing condition that we're imposing on the design of the structure. If we wanted to see a deformed shape of the mat, I'll go back and turn on the Z direction. For any contour, mainly for deformation, we can look at a warped view of this slab. So if I go up here to visibility after selecting the contour, we can select render model, and under the rendering options we have this option to warp the rendering. Now this warps it just as a 2D kind of folded membrane in this case. I can also extrude the mat by using this option for deformed shape, and this just gives a relative view, I guess, of the deformation in that slab and helps a user just validate the general deformed shape that might be expected under the loading conditions. One other thing that a user can do is for any contour we can right click and we can modify the range. So if I want to see deformations between, let's say, negative 27 and negative 15 millimeters, we can change the range, reset, and the program will redraw the range that we are interested in for this particular contour. To reset it, we would come back to reset and do this. We're now going to take this a step further, and I'll go ahead and turn off these results. We're going to generate design strips. So for this model, we want to have column and middle strips in order to design the slab for reinforcement. In order to generate the column and middle strips, there are two options really. The first option is to have the program generate these automatically, and to do so we need to enter the column strips. Once I enter column strips, maybe these strips look something like this. The program will automatically enter middle strips, subdividing these regions into middle strips. Okay, and we would do that in both directions. Second option is if you want more control over the middle strips, we would turn off and disable the automatic generation of middle strips, and the user would then draw in both column strips and also middle strips. You would draw both of them in. To turn that off, because by default it does this automatically, we can go to Criteria, Analysis Options, and we can turn off column strip, middle strip here. We're going to go ahead and use the option for automatic creation of middle strips, and let's generate our support lines. So we'll go under floor design. This also could mean foundation design, flexural design, if you will, and we'll select create X direction support line. I'm just going to start out here somewhere near the slab edge, and I'm going to snap on these supports, and then I'll press enter, just stop that one there. I'll go from here over to here, enter. Maybe we have something along this path. I'll select snap to perpendicular, and we might have something also in this location here. So maybe I do something like this. It's really subjective. You know, the user may have a different way of setting up those paths. I'm actually going to leave that as is. There will be a middle strip created along this column anyway, so we'll pick up just the change in deformation and change in stress at that particular location, where we might go from a positive bending or negative bending to a positive bending region where we have a support and a heavy load. Okay, we're going to go ahead and start this here. Let's go ahead and create another one. And you can see I'm a little bit loose in how I model these endpoints. I'll come back and clean them up and snap them to the slab edges. So if we use snap to perpendicular, we can come back and just move these to slab edges. They really don't need to be moved technically, but if you want to see them, I guess, more cleanly identified and have everything perpendicular, let's say relative to these global axes, you could post modify the endpoints like so. Okay, these ones I'll just stretch out, maybe there and there. Okay, that's the X direction. You'll notice if I generate the design cuts, the program generates several strips. So this is strip 1, strip 2, strip 3, 4, 5, and 6. Now for this model, this model is being done using the 2019 version, where the middle strips at the current time are not being generated. This has not been hooked up yet in this particular version. So I'm going to go ahead and model in those strips. Now, another option would be to use the old generator for design sections. This is actually what's used in version 18 and prior. So if we delete these, we have two options. I could draw them in, or I could use the old method. Notice when I use the old method, the program creates middle strip, like so. Okay, we have some areas here where this kind of sneaks past this region down to this face. Because this stops here and this stops here, there's a gap. And the middle strips are only replicated over the distance of the adjacent column strips. So one way to clean that up in the 2018 and previous versions would be to add what we call splitters. And I'll go ahead and I'll use a splitter, which is really just a virtual boundary to generate, let's say, more expected middle strips, or to manipulate how the middle strips are being generated. So I'll add a splitter along this path and along this path. I'm also want to make sure that these are closed off. on the ends. Like this one, if we're going to use the old method, this has to be closed off at the perimeter of the slab. In the new 2019 version, that's not true. The program can handle a support line node that actually stops prior to snapping to the slab edge. So we're kind of running under the premise of two different versions of the program in this case. So we'll go back and we'll kind of use the 2018 logic for the design strips here. So we'll create a splitter there, and then one more splitter. We'll use snap to intersection, something like that. Okay. I'm going to bring this back so it intersects there. And we'll go ahead and generate these again. And now you can see this cleanly stops at this location. Same thing here, that stops at that splitter. This stops right at the splitter, and that happens here also. So we'll use these strips. Again, if you don't like the way that the middle strips are produced from the automatic generation, we can turn that off and just draw in our own support lines for middle strips. We're now going to turn off the visibility. I'll use this option here from strip results / visibility. We'll turn off the visibility of the design strips and also the splitters. And I need to do the same thing really in the X direction. So we're going to generate Y direction strips. Okay. We'll have a middle strip generated along that column again, so we'll leave that column as is. Just snapping on the endpoints of the walls there. And for this one, we're just going to go right through that opening. Why am I going through the opening? Well, the purpose of strips is to generate design cuts. So really all we want are design cuts aligned, somewhere out here to produce a result for this region. And so by doing this, I could have terminated this here and here, and then the middle strip, I guess this would have reached all the way over when we produce the cuts. I want this to be broken in half, where part of them go to this side, part of them go to this side. So I'm bringing that straight through to make that happen. Okay, we'll exit out of that. Now we're going to generate our both directions. So we have the X direction. I can isolate directions. I'll turn off X, and I'm now left with my Y direction. So here we have middle strip, column strip for the Y direction. Notice that every strip, when we create the strip, it actually has a design criteria associated with it. So from design, you can see these are set to two-way slabs. The design section options give the user the ability to change where the design cuts start relative to a support, how many sections are in each span, or what is the spacing of the sections. Tributary width limits, this is new to version 2019. So the user could dictate to which side, each side of the support line, how far the tributary width is going to be for a given support line. So those are new options coming in version 2019. But once we have our design strips generated, now it's time to actually design the strips. Before we do that, we're going to check punching shear. We could have done this also after we checked our bearing pressure. So I'll do that first before I actually design these. I'm going to go back to my default display. We're going to go ahead and execute the punching shear check. And to get results for punching shear, after we produce the check, we'll go to loads. I need to set this to a strength combination. Otherwise, we will not have the ability to access the graphical results. So we'll go to strength, the envelope of strength, let's say. Under analysis, I'm going to collapse this by selecting this option, collapse all. We'll go to punching shear, and we're going to look at stress check. And we can see clearly there's several columns that say exceed code. Let me go back, and that's too thick of a line, so we'll just kind of mark some of these. These ones are exceed code. That's this red color that you see that indicates that. And if we look at one of these columns, let's say column 4, for example, if I dig deeper into that result set for column 4, and I'm going to go to Reports, we'll go to Punching Shear, Excel Report, and for column 4, we can clearly see at which critical section the check actually starts to make sense in terms of being below the allowable maximum by code, meaning where does the program produce sections where it does not exceed code? Okay, and if we look at the stress check, we'll go down here to column 4. You can see the current status is exceeds code. This is strength dead and live. That's the combination. And we can see that at the first critical section, the program's checking 9 critical sections on the perimeter of that column. Only the first critical section doesn't pass code. So that might indicate to the user, if I go back to the section geometry for column 4, the first critical section is at some distance away from the face of the column, and that's indicated here. There's a design length, and then there's a distance. This first critical section distance is 201 millimeters away from the face of the column. So that might give the user an indication of where you might need a thickening. So for this column, I might say, well, I'm gonna create a thickening at 250 millimeters from the face of column, and we know if we create that thickening, we're going to have more critical resistance to the punching shear, and we might pass and not exceed code because our allowable, the allowable maximum per code is no longer violated due to that increase in the critical resistance area. Okay, so that's how you can use that set of Excel results to evaluate this for punching. Now, where you do get an exceeds code mark, the program will not design reinforcement for you. It just gives you this error warning, exceeds code. It's up to the user to determine what to do with those particular columns. All of the other columns that say reinforce, the program would give you reinforcement. So we can check stress ratio. Let me go ahead and turn stress ratio on, and this gives us the ratio for each, let's say, bending about the local axes separately, about R and S. And we can see some of these high ratio values for the exceeds code columns. This will also show us the condition. How is it being checked? Well, blue is an interior column. There's 4 critical sections, 4 critical sides, basically, for a critical section. The orange is end edge, which is a 3-sided critical section. Yellow is actually a corner condition, so we have a few yellows. And finally, we can also look at kind of a shorthand abbreviated version of the reinforcement. This basically shows us, for example, that we need 8 total rails, 2 per side. It shows us an arrow to scale of how far out the shear reinforcement will be extended. And there are 9 studs at 65 millimeters on each rail. And the total rail length is 585 millimeters. So for those columns that need reinforcement, this is what the program produces in terms of a graphical report. If we go to the punching shear reporting again, I can use this punching shear reinforcement for the outcome of rebar, or let's say headed studs for the reinforcement for those columns. Okay, now we're going to generate the flexural reinforcement. So we're going to go back to floor design. I've already generated the design strips. We'll generate them again just to show that. And I'm going to design those strips. We've analyzed, generated the strips, and now we're designing the strips. The strip design is done. Ultimately, we want to see what the reinforcement is in the strips, and this is what we call calculated rebar. It is in addition to the base rebar that was entered by the user. Base rebar is also known as user-defined rebar. So if I go to the rebar tab, or I could also go to floor design, and I calculate the rebar, this allows me to produce a graphical drawing of the program calculated reinforcement for the mat. We could produce it per envelope, meaning minimum reinforcement and strength. It takes the envelope of those cases. I could produce an envelope of only service or minimum rebar, strength rebar, or individual combinations. Okay, we'll select OK, and we can see this requires quite a bit of rebar. The green rebar is rebar that is placed at the bottom of the slab. The red rebar is top rebar. Blue rebar could be either. Blue rebar indicates, and let me turn off the design cuts, and we'll just take a look at this bar here. Blue reinforcement indicates that the bar is extending through two different thicknesses of components, basically. So you can see this bar starts here in the 600 millimeter thick slab, and it actually ends in plan, it ends in the 450 millimeter slab. So if we look at a cut through there, if this cut looks something, you know, like this, and that bar is intended to be relevant relative to the effective depth from this slab upward, then there's a chance it could be sticking out of the slab below the 450 millimeter slab. That's why it's indicated as blue. It's really just a warning to the user, check those bars for detailing of the bar or placement of the bar. Okay, so these are the reinforcement outcomes for the strips. Now notice we have bars that are skewed basically at some angle relative to the global axes. They are always by default aligned parallel with the support line. We're going to isolate bars. So if I go to the rebar tab under Display Manager, I can control how these bars are displayed. I only want to see, for example, the Y direction bottom bars. I'll turn off the X direction. I'll turn on Y direction bottom only. And I'm going to turn off base rebar. I know that the base rebar I have in the model is the mesh reinforcement, so we'll ignore that. Now I only want to display these bars here. So this gives me the ability to display, isolate display of the bars, and I could actually export this rebar set up the appearance settings for exporting it as a DWG. Once I set this up, then I can go to File, Export. I could actually export this to DWG, or I could export it as an IMP file and import it into something like Revit if we had this foundation system in Revit and maybe it stemmed from Revit. If I import a model from Revit, produce the rebar, I can always export the model back into Revit. So that's the only workflow available. I could not import rebar into a non-existent Revit model, meaning a model that the builder model was not created from. So if you want the rebar to be aligned orthogonally, once I go back to floor design, if I regenerate the bars, you'll notice this bar orientation. I can say angle this relative to the global axes. And here we're going to do this from 0 degree and 90 degree, and the program will adjust the number of bars required. And we have something now that looks like this. If I come back and go back to my display manager and produce again only the bottom bars in the Y direction, we get a layout that looks something like this. Okay, so that's how we produce the reinforcement for our design strips. Now, the user might be interested in the actual results of the design strips. So coming back to floor design, if I look at the X direction, for example, I'll turn on the design cuts. And in the result settings, I want to look at the, let's say, the moment diagrams for strength, dead and live. So I'll set this combination to strength, dead and live. I'll select analysis, design sections, and we can look at deformations on the design cuts. I can look at actions, for example. Here we're looking at the bending moments. We would produce bending moments. We could produce stresses if there's any post-tensioning. Balance loading applies really only to post-tension design. Stresses, that would apply to PT design. And investigation would allow the user to generate the moment capacity and demand graphs along the design strips. Okay. If we double click on any design cut, we can actually produce an individualized report for that particular design cut. So this shows me some of the geometrical properties of the cut, the base rebar, the idealized image here, which shows a graphical representation that we need top bars, and it gives me more information on the reinforcement and moment capacity. That will conclude this brief tutorial of Adapt Matte. If you have any questions, please contact support@adaptsoft.com. Thank you.